Our next application of differentiation are optimization problems. I've mentioned these earlier, how these are used in many types of applications, that they're a very important type of problem. And we've looked a little bit at how to approach these problems by finding the either local max and min or absolute max and min of a function. So in this section, we'll be looking more in detail at word problems that involve using calculus to find optimum values. Here I'm going to present some steps that are useful for approaching optimization problems. Before you even start this, though, you need to recognize that you're dealing with an optimization problem. So if you're presented with a problem where your goal is to find the maximum or minimum of something, right, or the greatest or smallest or best or most efficient, right, those types of words clue you that this is an optimization problem. So these steps will give you a general strategy you can use, and that's often helpful if you're not really sure how to get started with the problem. So step one, understand the problem. So that means read the problem carefully, maybe even multiple times. Then start asking yourself, what is the unknown? In other words, what are you trying to find? And what are the given quantities and given conditions? And we'll start writing these down as we go through the later steps. But you want to start getting acquainted with the basic framework of the problem. Step two, drawing a diagram. So usually this is helpful, just to draw a figure that describes the situation, and start labeling what you can on that diagram, including the given information. So as you're doing step two, step three might sort of overlap with step two, introducing notation. If we're going to use math to solve this problem, we have to have variable names representing different aspects of the problem so we can use them in our equations. So you'll need to assign a name to the quantity that you're optimizing. So usually you'll select it based on what it represents, right? If you're maximizing profit, you might use the letter P for profit. Or if you're minimizing cost, you might use C. For now, in our steps here, we'll just call it Q for quantity. There might be other unknowns that you'll also need to name those with various variable names. So all of these can be labeled on your diagram with the names you've given for those particular pieces. So in the next few steps, we're going to start creating the function that we're going to find the max or min of. So that function should represent whatever it is you were asked to optimize, which we've been calling Q. So eventually we're going to write Q as a function of some variable x, where x represents some aspect of the problem. So in step 4, you'll make your first attempt at expressing Q, writing an equation for Q. So you'll have to use the given information about the problem to help you write that equation. Now it may not yet be in the form we want, and the main issue is if Q has been expressed as a function of more than one variable. So suppose Q equals some expression that has x, y, and z in it, right? That's not in a form that we can use calculus on at this point to optimize. So in step 5, we're going to deal with that. So what you want to do is use the given information in the problem to write one or more equations that are different from the equation you wrote for Q. And these equations will relate some of these other variables that are appearing in your equation. And then you want to manipulate those equations to be able to substitute back into your formula for Q until you are able to write Q as a function of one variable only. Okay, so once you have this function, then the problem is similar to problems we saw on the section on finding local max and min or absolute max and min, involving the critical numbers, etc. Right? So use those methods to find, assuming they're asking for absolute, right? Look, find the absolute max or min. And so usually when we're finding absolute, we used the closed interval method where we tested the critical points and the endpoints as possible candidates. Let's look at this example. We're told a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So if we first just started thinking about the problem as we're reading through it, it might help to make a few sketches or at least visualize in your head some possibilities for how I could construct this field. So one example we see here, right? Notice we've chosen dimensions here just as an example. So the total amount of fencing in red adds up to the 2,400 feet. Right? So 2,200 plus 100 and 100 more gives us the 2,400 feet. Remember, we didn't need any fencing along the river. And then down here we've calculated the area. So it'd be 100 times 2,200, so there's the area of that field. And then we try an alternative, right? We could choose to design the field this way. So the 3 lengths of fencing still add up to 2,400 feet, but the area is going to be different, right? 700 times 1,000, we get a different area. And then here's a third possibility. We've chosen different dimensions that still add up to the total of 2,400 feet. Calculating the area, 1,000 times 400. Now there's lots of other possibilities, right? Infinite number of possibilities. These are just 3 samples just to get us thinking about the problem. Now compare the areas though, right? They're very different. Out of these 3, the middle one has the largest area. But this may not be the optimal, right? There may be some other choice that has even a bigger area than this. So we need to make sure we find the one that gives us the absolute largest possible area. Okay, so step 1, part of it was reading through the problem, starting to look at what's, identify in your mind what's given and what you're wanting to find. So basically what was given was the type of field that's being constructed and how the fencing will be used, and really important here, the amount of fencing that we'll be using. And then the unknown, the thing we're trying to find, is to determine the dimensions of the field that maximizes the area, right? This here, the largest area, this word is our clue that this is an optimization problem. Okay, so let's, before we go on to step, well, I guess part of step 2 actually is making a figure that's more generic, right? These first few figures were just sort of playing around at different options, but let's make a figure that we can use throughout the rest of the problem solving. So here's the river here, and then our fencing will be something like this. And let's start labeling things. So we don't know the dimensions, right? That's actually what we're trying to find. What are the dimensions that maximize the area? So let's just give names to these. You can call them whatever you want. Let's let X be that length and Y this one. And then if we wanted, we could label the area is in this region here. So that will get us started, and we've actually already started on to our next step 3, sort of combines with step 2, labeling the variables involved in the problem. I guess we could go ahead and start that here. So the amount, the thing that we're trying to optimize is area. So you need a name, a letter name for area. So we've actually already put that in our figure. So let's just say here we want to maximize area, and we're going to use the letter capital A for area. Some other variables, you can see we identified them when we made our picture, and it's just the two dimensions, right? So one of them is x, the other y. Okay, so now we'll continue on the next slide with the next step in our problem-solving method. The next step in our method is to express the thing you're trying to optimize, which in this case is the area, as an equation, or in an equation. So A equals blank. See if you can write what goes in the blank. And usually your figure, and oftentimes your figure will be helpful for this. So in this case, since A is the region is a rectangle, the area will just be x times y based on the picture that we have there with the dimensions labeled as x and y. Okay, so that's all for that step, which was number 4. Now step 5 is to look at your equation and see if, in this case, area is expressed as a function of one variable or more than one. So here we can see on the right of our equation there are 2 variables. So that needs to be addressed. We need to substitute for either x or y to get the right side to have only one variable, not 2. So we need to rewrite in terms of one variable only. Okay, so that's what step 5 is about, trying to accomplish that. So now we start thinking about other equations that are different from area. So let's just try to come up with one. Now for this, it will either come from your figure or from given information, or maybe both. So there is some given information we haven't used yet, and that has to do with the total amount of fencing is 2,400 feet. So let's see if we can write an equation that expresses that. So looking at our figure, the total amount of fencing will be x plus y plus another x. Okay, so the total fencing, we have x plus y plus x, and that needs to equal 2,400. And we could simplify that by combining the x plus x to 2x. So 2x plus y equals 2,400. So now, what do we do with this equation? Remember, our goal is to substitute for either the x here or the y here. So that means one way we can do that is to take this equation and either solve it for x and substitute it in here for x, or solve it for y and substitute it in for y. Either way would be fine. This looks a little bit easier to solve for y. All you have to do is subtract 2x. So let's do that. So we get y equals 2,400 minus 2x. So now we're going to take what we just found for y and substitute it in right here. Okay, so we're going to now rewrite our area equation equals xy, and then substitute in, so x times, replace the y with 2,400 minus 2x. And then let's do one more simplification. So now we have a equals, if you distribute the x, 2,400x minus 2x squared. And now if you wanted, you could call this a of x using the function notation, because we've achieved our goal of writing area as a function of only one variable, and it happens to be the variable x. So that completes step 5. This is an important step. So the next step will be to maximize this function. In other words, find the absolute max of this area function. Now for absolute maximum, remember our method for that was the closed interval method. And part of that method is you have to have a closed interval that your function is defined on. That was not given to us. We need to think about this problem to find that interval. Now notice a is a function of x, so that means the interval needs to be for x. Now in our picture you can see where x is, right? It's this dimension. So let's think about the smallest x could possibly be and the biggest it could possibly be based on the constraints of the problem. So it's pretty obvious the smallest x would be 0, right? So that's going to be our left endpoint. Now think about the right endpoint. There is a maximum x could be because we only have 2,400 feet of fencing. So since there are two lengths with x, half of 2,400 is 1,200. 1,200 is the biggest x could possibly be. Now you might think that in that case, right, y would be 0 in that case. So the two lengths would actually be right on top of each other. So you might think you should be able to use 2,400 feet for that dimension. But think about what happens if you just barely space them apart. So you make a long x and a long x and then a very narrow y. The two x's, right, if you tried to make x say 1199, or sorry, let's make it, yeah, let's do that. So then when you add that to the other 1199, you're already close to 2,400, right? And then that piece would finish it off. So that tells us if we keep shrinking and shrinking, the biggest x can be is 1,200, right? 2,400 for x wouldn't work if you started to space them just slightly apart. You'd have two lengths that are close to 2,400. Okay, so now we have established our function that we want to find the absolute max of and a closed interval for x. So the next step is just to use what we've already learned in a previous section using this closed interval method. We'll do that on the next slide. So as we just saw, our goal now is to find the absolute max of this area function over the closed interval 0 to 1,200. So we're using the closed interval method, and the first step of this method is to find the critical numbers. Okay, so to find critical numbers, we need the derivative of our function. So this is a very simple derivative. We get 2,400 minus 4x. And then there are two ways we can get critical numbers. One of them are the values that make the derivative 0. The other are the values that make a prime undefined. Okay, so let's start by setting a prime equal to 0. So just copy here the formula we found for a prime. Set it to 0. When we solve this for x, right, we'll first get 4x equals 2,400, and then divide by 4, we get x equals 600. So that's a critical number. Now we'll look at values that make a prime undefined, but a prime is a polynomial, so it's defined for all x, so we don't get anything there. So now our candidates for the absolute max and min, we only need the max, but these are the candidates for both. We make a list that includes our critical numbers and the two endpoints. So we only had the one critical number of 600, but then we have the two endpoints, 0 and 1200. And then you take all of your candidates and you plug them back into the original function. So we need the formula for A, which was on the previous slide. That formula was 2400x. Oh no, it's up at the top. We see it there. I'll just copy it again. 2400x minus 2x squared. So let's start with A of 600. Okay, so you get 2400 times 600 minus 2 times 600 squared. And when you simplify that, you get 720,000. Okay, next we'll plug in 0. That one's pretty easy. You'll get 0 minus 0, which is 0. And then the third number we plug in is 1200. Okay, so 2400 times 1200 minus 2 times 1200 squared. Simplifying that, you get 0. So now compare the three output values we get. And whichever one is, we're only interested in absolute max. So the biggest of the three is this one. Okay, so now let's take that information and clearly answer the question. Right, so the question here was, find the dimensions that give us the maximum area. So the 720,000, that's the area, right? That's A of 600 equals this. We want to find the dimensions. Well, the x is what we plugged in, right? The 600. So an x dimension of 600 gave us the maximum area. So we know x is 600 and we should put units on it, right? So remember here our distances were being measured in feet and x is a length, right? But what about y? We need to give that also. So think back to your picture. We had x and y, and this of course is another x. And actually we don't even need the picture. It might be fastest to think back to the equation we wrote that relates x and y. So we wrote this equation on the previous slide, and that was 2x plus y equals 2400. Right, that was the equation that expressed the total amount of fencing as 2400 feet. And then we solved it for y. 2400 minus 2x. So what we can use is this equation and substitute in 600 for x to find what the corresponding y is. So 2400 minus 2 times 600. Right, so that's 2400 minus 1200, which gives us 1200 feet. Okay, so the dimensions, and you need to say which is which, right? Because if you just say 600 by 1200, that's not enough information because one of them is coming, we have 2 copies of, and the other we have only 1 copy of, so you have to be clear. So it might help to label them on your picture, right? So this should be 600 in that direction, 600 feet. And then the y, this direction should be 1200 feet. And the area that results from that, I mean, you could find it by multiplying 1200 by 600, or we actually already know it. It's up here, this absolute max for the area. That's what you would 720,000 is exactly what you would get if you multiplied those two dimensions. So I'll just put in here area equals 720,000, and then the units there would be square feet. So if you remember back to the very beginning of this problem, we sketched 3 possible dimensions that could be used. The one that we found that had the largest area, the area turned out to be 700,000. So by going through this method, we found there was the one that is optimal is actually better than that. It has an area of 720,000. So you can see in this example how we first recognized this was an optimization problem, and then how we worked through the 6 steps we presented for approaching those types of problems. Here's another example. So let's start by reading through the problem. You've been asked to design a 1-liter can in the shape of a right circular cylinder. Find the dimensions that will use the least amount of material. So as soon as you see that phrase, least amount, we know this is an optimization problem. And it might be helpful to go ahead and figure out what are we asked to maximize or minimize. So here, material. So we want to actually minimize the amount of material. So that tells us we're going to need a function that tells us the amount of material. Okay, so that will be one of our steps as we go through the process, is getting to that function, and then once we have a function for the amount of material, we can use our optimization methods. So let's go through the 6-step process we've been using. First of all, make sure you understand the problem, right? Read through it a few times if you need to, and start writing down what's given and what you want to find. So this one's a pretty simple statement of the problem, right? We're given that we're designing a 1-liter can, right? So the volume needs to be 1 liter. And we were given the shape, right? It's a right circular cylinder. That's the basic given information. What we need to find, we've already discussed, we need to get a function for the amount of material, which would be the surface area. And then once we have that function, we can then minimize it. And then let's look at the exact question. Find the dimensions. So then find the dimensions that achieve that minimum surface area. So I'll just say find the associated dimensions. Okay, so now we have kind of a feel for the problem, what was given, and what we want to find. The next steps, 2 and 3, kind of go together, and that's sketching a figure and start giving names to your unknown variables. So obvious sketch here is a right circular cylinder. So circular cylinder means the base is a circle. Right means the sides go up perpendicular to the base, right? So it's your standard cylinder shape that we usually think of. So let's start labeling the variables here. So the dimensions that we have to decide on, one would be the height, right? So let's call this dimension here, right? That's obviously the height. We'll call it h. And then the other thing we have to decide on is the radius of the circle that makes the base and also makes the top. I'll just label it up here at the top, right? That's our radius. So the dimensions we want to find are r and h, right? Now step 3 is to name the variables. So like I said, that kind of goes along with making the figure. But let's spell them out clearly here. So we've got r for the radius. And another thing that I didn't do in the previous example, but it could be helpful when you name your variables, is to go ahead and say what units you're going to be using for those. So if you look at the problem, there were no units given for length. So we could choose anything we wanted, but let's actually come back to that. We'll fill it in after we discuss the others. So h we've already labeled as another variable. That's the height of the cylinder. And then we were given the volume, right? So we don't really need a variable name for that because it's fixed at 1 liter. But let's just make a note. It's going to help us figure out the units. So the volume is 1 liter. And so we know 1 liter is equal to 1,000 cubic centimeters. And that is going to help us decide our units, right? If volume is in cubic centimeters, that means lengths are measured in centimeters. So that's going to be the best choice for units for the radius and the height. Now there's another variable we need, and that, if we look through our list of what we need to find, right, we need to find the surface area. So we'll need a variable name for that. So how about we just use A for area? So that represents the surface area of our can. And the natural resulting units would be square centimeters, since we're measuring lengths in centimeters. Okay, and like I said, we don't need to use V for volume because the volume is fixed. Okay, so I think that's good for listing the variables. So now we can start writing our equations that are using these variable names. So remember, our goal is to get a surface area function. So our next step will be to make our first attempt at writing a formula for the surface area. Now we're going to try to write our equation for the surface area. So looking at our figure, the surface is made up of multiple pieces. So we've got the base is a circle, the top is an equivalent circle, and then there's the sides. Okay. So let's work on those pieces. So the base area is just use the formula for the area of a circle of radius r. So that's pi r squared. But the top is the same, right? So we're going to multiply it by 2 for the top. And then we have the sides. So to find that, what we can do is take the perimeter of this base and multiply it by the height. Okay, so the perimeter, of course, we know that formula is 2 pi r, and then multiply it by the height, which is h. So the total surface area will be all of those pieces added together. So we take the base area times 2, that's 2 pi r squared, right? Multiplying by 2 accounts for having both a base and a top that are the same area. And then we add to that the surface area of the sides, 2 pi r h. So the next step is to look at your equation that you just wrote and see how many variables are on the right. We want to get it down to 1 variable on the right. And you can see we've got 2 variables, r and h. So we need to eliminate one of those, either r or h. Now to do that, we need another equation that's unrelated to the area of the function that we just wrote. So we need a new equation that involves the 2 variables r and h. So think about, is there something from the geometry that we could write, or is there some given information we haven't used yet? And there is an important piece of information we haven't used yet, and that is the volume has to be 1,000 cubic centimeters. So that has to be used at some point in the solution, right? So to write this in equation form, we need a formula for the volume and then set it equal to 1,000. Okay, so the volume of this cylinder here can be found by taking the base area times the height. So the base area is just the area of that circle, pi r squared, times the height. Right, so that tells us we've got pi r squared, h is the volume, and we're setting that equal to 1,000. So now we have our new equation, and remember what we want to use it for is to somehow plug it back in here to get rid of either r or h. So that means we can solve it either for r or h, either one, and then whichever one you solve for, substitute it in back here. Now looking at this equation, it's going to be easier to solve for h, right, because the r is squared. So I'm going to choose to solve it for h. So h equals 1,000 divided by pi r squared. And now we're going to rewrite our A equation, and everywhere we see h, we're going to substitute. So we get 2 pi r squared plus 2 pi r times this h, so here we replace h, and now we've achieved our goal of eliminating one of the two variables. Now the area is written as a function of only the one variable r, so we could call it a of r instead of just a if we want to use that function notation. So let's simplify this a little bit. Keep the first term, 2 pi r squared, and on the second term, notice that the pi's will cancel, and then one factor of the r will cancel. So we're left with 2 times 1,000 in the numerator, so that's 2,000. And then the denominator, one of those r's canceled, right? So it's just r in the denominator. Okay, so this is our surface area function. And it's a function of only one variable. It turned out we wrote it as a function of the radius. Okay, so once you have that step, then what's left is to find the absolute extreme value you want. In this case, we wanted to minimize a, so we need to find the absolute minimum of our area function. Okay, so we want to think about which method we want to use, the closed interval method or something else. So if you use the closed interval method, you're going to need an interval for r, since a is a function of r. So you'd have to think of what is the minimum possible value for r and the maximum. Minimum is clearly 0, and you probably could find a maximum, but it's not really obvious based on the constraints. So let's think instead about just finding a local minimum, and then we could think about whether it's also the absolute minimum. So we're going to attempt to start by finding local minimum. So the choice for methods there, they all involve critical numbers, right? And then once you have your critical numbers, you have a choice of 2 methods. So let's continue on the next slide by finding our critical numbers. So here's the area function we just found, and we discussed that we want to use the method to find local min. Then we'll try to verify whether it's an absolute min. So critical numbers are necessary no matter what method we're using. So to find critical numbers, we need to first find the derivative. So on the first term, carry along the 2 pi, it's a constant, and then for r squared, we use the power rule. So you bring the 2 down, and that gives us 4 pi, and then you reduce the power from 2 down to 1. Now on the next term, we need the 2,000 can just be carried along. And let's discuss the derivative of 1 over r. We actually did this earlier. We used x and 1 over x, right? But same idea. You can rewrite 1 over r as r to the negative 1 power. That way you can avoid the quotient rule. And then using the power rule, we bring to the negative 1 in front, reduce the power by 1. Rewrite this as negative 1 over r squared, right? So we've seen this before. So let's come back to our derivative. We already took the derivative of this term, it's here. And then the derivative here, carry along the 2,000, and then it's multiplied by negative 1 over r squared. So altogether that's minus 2,000 over r squared. Now to find our critical numbers, we want to set a prime equal to 0. So I'm just going to copy our formula here for a prime. Set it equal to 0. Now let's solve this for r. So I'm going to first add the fraction over to the right side. So now the left side is 4 pi r, the right side is positive 2,000 over r squared. Let's multiply both sides by r squared next. So the left becomes 4 pi r cubed, and the right side is just 2,000. We're trying to solve for r, so let's divide by 4 pi next. So r cubed will be 2,000 over 4 pi. Now 4 goes into 2,000, 500 times, I think. Okay, so that becomes 500 over pi. And then take the cube root, we get r is cube root of 500 over pi. And if you wanted to get an idea of how big that is, put it in a calculator and it comes to about 5.42 rounded off. So now the question, is this a max or a min at this critical number, right? We only have the one critical number. Or it could be neither, right? So here's where we have the options, right? We've learned two methods to determine this. One is to use the first derivative and the number line method to determine where the function's increasing and decreasing, and then you can tell from there whether it's a max or a min. The other option is to use the second derivative test. That might be slightly faster. So let's use that. So we're going to need a double prime. So look at the formula for a prime and take its derivative. Right, so up here, the first term, a constant times r, the derivative is just that constant, so that will be 4 pi. Now the next term, you can use similar method where you rewrite this as r to the negative 2. Right? Let's see if we can visualize this without having to write it. So it's 2,000 times r to the negative 2. So you keep the minus 2,000. And then for r to the negative 2, you bring the negative 2 down in front. That makes this plus 4,000. And then you reduce the power by 1. So it was r to the negative 2. Now it's r to the negative 3, which is the same as putting r cubed in the denominator. Now we plug in our critical number, which is the cube root of 500 over pi. Okay, so plugging that in, we get 4 pi plus 4,000 over, now this is convenient because we're cubing this input. So the cubing just gets rid of the cube root, so it'll just be 500 over pi in the denominator. Now to simplify this, let's keep the 4 pi. Take the numerator 4,000 and multiply it by the reciprocal of what's in the denominator, pi over 500. Simplifying again. So 500 into 4,000 is 8, so that is actually 8 pi. And we get 12 pi, but all we care is that it's positive. Okay, so we get a positive second derivative, which means concave up, so the shape is like an upright bowl, and that tells us at our critical we have a min, not a max. Right, so there's our answer to that question. So now we've arrived at, we've done the optimization, but we want to make sure we summarize our result appropriately and make sure we answer the question that was asked. So we'll do that on our next slide. So we just found that the area is minimized when the radius is the cube root of 500 over pi, which is approximately 5.42, and that would be in units of centimeters because we already decided the units of r was centimeters. Now the question was, find the dimensions. So we're partway there, right? There were two dimensions, the radius and the height. The dimensions that minimize the area. Okay, so we know one of them. R is this approximately 5.42 centimeters, but what we also need to know the height. Now if you look back 2 slides, we wrote this formula for h. It was 1,000 over pi r squared. So we know what r is for to achieve our optimal value, so we can just substitute that in to find the corresponding h. Now the exact value, you'd plug in the actual unrounded expression, right? Cube root of 500 over pi. You could simplify that if you wanted, but it's pretty messy. You could leave it like that. But for a practical use, we'll need to put this in a calculator to get an actual measurement we can use. And that comes to about 10.84. And the units for h was also centimeters. So the dimensions that should be used, just to clearly state our answer to the problem here, we should use a radius of 5.42 centimeters and a height of 10.84 centimeters. And this design will achieve the goal. It will result in having a volume of 1,000 cubic centimeters, which is 1 liter, and it's the best choice of dimensions for minimizing the surface area. In other words, minimizing the amount of material used to construct the can. The next example we're going to look at is related to business and economics. So first, I want to introduce some terminology in this area. So we'll start with a cost function, which we'll be calling C of x. X represents the number of units being produced, so not the number sold. This is referring to the cost of producing X items. And C would be the cost to produce X units. Then the term marginal cost. We'll be seeing this word marginal used again, and it always refers to a rate of change. So marginal cost is the rate of change of cost with respect to the number of units. Rate of change, we know, is the derivative. So the marginal cost can be found by finding the derivative of the cost function. So the next function we want to introduce is having to do with selling the items, right? So C is the cost to produce the items, the manufacturing costs, and P is the price per unit that they sell to the consumers. So again, X is the number of units, and P, notice it's not the total price, it's the price per unit. So if you think about this, and we call this the demand function or the price function. So if you think about the cost per unit, if a large number of units are produced, in general, they can afford to sell the item at a lower price. So usually this demand function is decreasing. As the number of units X gets larger, the price per unit would get smaller. Next, we can talk about revenue. So revenue is the amount of money brought in to from the sales. It has nothing to do with the costs of manufacturing the items. So let's think about how we could calculate revenue, the amount of money brought in. If X units are sold and they're charging a price given by this function P of X, then we can calculate the total revenue by taking the number of units produced, times the price per unit. And so the quantity of units is what X is, right? So X goes in for quantity, and then price is represented by P of X. So the revenue function, R of X, has this form, X times P of X. Next, we can talk about marginal revenue. So we discussed earlier that marginal means rate of change. So the derivative of the revenue function would give us the marginal revenue. Next term is profit. So most of us are probably familiar with this idea. The profit would be the total amount of money brought in through the sales minus the amount of money spent to manufacture the items. So in other words, the profit would be revenue minus cost. Okay, so we have our profit function and then the term marginal again. So marginal profit would be the derivative of the profit function. So now that we have all this terminology as a background, we can do some optimization problems in business and economics. Let's read the problem for this example. A store has been selling 200 TV monitors a week and charging $350 each. A market survey indicates that for each $10 rebate offered to buyers, the number of monitors sold will increase by 20 a week. Find the demand function and the revenue function. And then answer this question: how large a rebate should the store offer to maximize revenue? So notice the word maximize, right? This tells us this is an optimization problem. And the thing we want to optimize is revenue. So we're eventually going to need to find a revenue function and then use our optimization methods. But notice they kind of gave us some help by saying first find the demand function and the revenue function. So we're going to find revenue function there. And then we can proceed with the optimization. So let's start thinking about the problem, right? Step one of our strategy, make sure you understand the problem, and then start writing down what you know and what you're asked to find. So let's make sure everything's clear in the problem. So the first sentence is pretty clear, what they've been doing. So then it talks about this every $10 rebate. So in other words, if they reduce the price by $10, they would sell 20 more TV monitors each week. And then they could do another $10 reduction and they'd sell 20 more, right? So the question is, if they keep the high price, they're not going to sell as many TVs. If they lower the price, they'll sell more TVs. So we want to figure out exactly how much should they lower the price so they make the most revenue, the largest revenue possible. Okay, so let's just write down some of the given information. So currently they're selling 200 monitors, I'll just say units per week, and they're charging $350 per unit. Okay, then we have this information about for every $10 reduction in the price, they will sell 20 more units per week. Okay, and then what's unknown, what we need to find, they gave us some help here. We want the demand function. Remember, that's also known as the price function, price per unit. And then also, we'll call that P of X, right? And then we also want to find the revenue function, which we call R of X. And then the last question is, the next thing we need to do is optimize the revenue function. And actually optimize means the maximum. And the final question is, they're asking for about the rebate. So find the optimal amount of the rebate. Okay, so that's step one, just kind of thinking about the problem, what's given and what we want to find. Now steps 2 and 3 kind of blend together. We want to sketch a figure, but this one there really is no obvious figure to sketch, so probably we won't need to do that. And then step 3 is introducing notation. So we've already introduced the P of X and R of X. We didn't really say what X is, right? So X, just like we were discussing in the background, is the number of units. In this case, it's the number of TV monitors. And it's per week, right? Number of monitors produced and sold per week. Okay, so that is step 3. In step 4, we want to start writing our equations. Now, because we're asked to optimize revenue, right, the main equation we need is an equation for revenue. But remember, revenue is defined as X times P of X. So we have to find P of X first before we can find the revenue. So we'll work on finding these equations on our next slide. Let's now work on finding the demand function, which is what we're calling P of X, and remember it stands for the price per unit. So remember what we know, the current price is $350 per unit. But we're considering reducing the price. Okay, so the reduction, we were told for every 20 units produced, the price will decrease by $10. So it's subtract that amount, right? But this depends on how many units they produce, right? So the actual reduction in price will depend on the number of units, right? If they produce 20 units, the price would go down by $10. If they produce 40 units, the price would go down by $20, and so on. So let's start thinking about this. Our price that they're actually going to charge will be the current price minus the reduction. And what we know so far is the reduction is $10 per 20 units, but we need to multiply that by the number of units. Remember, X is the number of units. It's an unknown amount. They have to decide what that's going to be. And notice if you check the overall units here, units and units, that's really number of monitors, right? Those cancel, and we're left with dollars, which is the units we should have for the demand function or the price function. So now let's just simplify this. Oh, I just realized something. It's not X units. Let me explain this part more carefully. So it's actually, they're already producing 200 units. So that's sort of their starting point. So what needs to go here is not the total number of units, it's the number of additional units beyond their current level. Remember, their current level is 200 a week. X represents the total number produced, but what we actually need to multiply by is the number of additional units. So that is X minus 200. Right? So if they produce 210 units total, that means X would be 210. By subtracting 200, we would get 10. That's the number of additional units beyond what they're already producing. Okay, so now let's simplify our P of X. So we have 350 minus, so the 10 over 20 is 1/2 times X minus 200. Okay, and then we could distribute over the parentheses. So 350 minus X over 2 plus 100. And then you could combine the 350 plus 100. So we end up with P of X equals 450 minus X over 2. Okay, so that is our demand function. The next thing we were asked to find was the revenue function, right? So let's work on that. So we call that capital R of X. And as we discussed in our background before this problem, revenue is X times P of X, right? Total X is the total number of units produced. P of X is the price per unit. So by multiplying that, we get the total amount of money brought in by selling X units. So now we can substitute in this formula here for the P of X. So we get X times, and then we've put in our formula, 450 minus X over 2. And then for the final version, we'll distribute. So we get 450X minus X squared over 2. We now have our revenue function. Now the next step in our strategy is to look at your function for the thing you're trying to optimize, which is revenue, and see how many variables are on the right. If there are more than one, you have to do some work on that to try to reduce it down to just one variable on the right. But notice here there's only one variable, X, so we don't have to do any revisions to this. So there's only one variable on the right. So that part is good. We don't have to do anything else. So now we have the function we want to optimize. So we'll use our optimization techniques on this revenue function, and we'll do that on the next slide. So here's the revenue function we just found. We know we want to maximize this. So let's think about what technique we want to use. We really want the absolute max, right, rather than a local max. And for absolute max, we would use the closed interval method. But we would have to figure out the closed interval to use. And since R is a function of X, we need a closed interval for X. So we have to think about the problem to see if we could find a closed interval that makes sense in the context. Remember, X is the number of monitors that are being produced per week. So there's an obvious minimum, right? 0. But there's really no obvious maximum, right? There's no limit based on the problem that was described. There's no limit to how many TVs they could produce per week. So this method isn't really going to work out perfectly to use the closed interval method. Well, let's look at our function again. Notice it's a quadratic. So we know what kind of shape it has. It's a parabola. And if we make just a rough sketch of what this looks like, notice that it's, because of the negative in front of the x squared, it's been flipped upside down. So it's an upside down parabola. If you wanted to find the y-intercept, that means you plug in 0 for x. you get 0 minus 0, so y would be 0. So it passes through the point 0, 0, and it's an upside down parabola. Okay, so just to label our axes, we have x, and then this would be r, because r is a function of x. So even though we can't really determine the right endpoint for x based on the context, just looking at this function, we can see the vertex is where our absolute max is. Now back in pre-calculus, you would use a formula or a method of completing the square to find the vertex. But here, we can still use calculus because that vertex is also a local max. And we know we could find that by finding the critical numbers, right? The points where the slope of the tangent is 0. So let's look for critical numbers. Okay, so that would be where the derivative is 0. So let's first compute r prime. So looking at the formula for r up at the top, we just take the derivative and we get 450 minus, now on this term, the over 2 is the same as multiplying by 1/2. So you just carry along the 1/2, bring the 2 down in front, reduce the power by 1. So we have 1/2 times 2x. So the 2's cancel, and we're just left with x. So this is r prime, and by the way, this is our marginal revenue function. It's the rate of change of the revenue function. We don't really need that. I just thought I'd mention the terminology. Now, to find critical numbers, we set r prime equal to 0 and solve for x. So we take our equation for r prime, set it equal to 0. When we solve for x, we get 450. Now in general, when you find a critical number, it's possible to have a local max there or a local min or neither. But we can see from this picture, we only got one critical number, so it has to be the one corresponding to this point where the slope is 0. So it has to be the one where we have our this local max. If you wanted to try to verify it's actually a local max rather than a local min, you could use, there's two options that we've learned. You could use the number line method where you use the derivative r prime to determine where the function's increasing and decreasing. Or you could use the second derivative test, and that one might be faster here. So let's find the second derivative. And that's pretty simple. Look at the formula for r prime. The derivative of 450 is 0, and then the derivative of minus x is minus 1. Then you plug in the critical number we're considering, which is 450. But notice it doesn't matter what you plug into this formula. The output is always minus 1. We got a negative second derivative, which means, right, think of that as concave down. And if you visualize concave down, that tells you you've got a max. Right, that's what the second derivative test tells us. So by the second derivative test, we know we've got a local max at x equals 450. Now remember, x is the total number of units. So to summarize this, we could say to maximize revenue, this company should produce 450 monitors per week and also sell them, right? But if you look back at the question was what rebate should they charge? Right? What should be, how large of a rebate should they charge to maximize their revenue. So we need to find what is the rebate that corresponds to this. To help figure that out, we can go back to our price function or demand function, P of x, and plug in 450 for x. We can't see this equation, it was on a previous slide, but it was 450 minus x over 2. So it'll be 450 minus 450 over 2. Right? And simplifying that, we get 225. Kind of running out of space here, but it's not really worth going to another slide. So let's move up here and write our final result. So they should charge the price $2.25 per set, per TV set, or per unit. We still haven't answered what the rebate should be. So remember that initially they were charging $3.50 per set. So all we need to figure out the rebate, just subtract, right? So $3.50 minus $2.25 gives us $125, and that would be in dollars, right? So the rebate should be $125 off. That's the question that they actually asked. So there's lots of numbers involved with this absolute max that we found. Right? Let's look at the numbers involved. The number of sets that should be produced and sold per week is 450, right? They could have asked that. How many sets should they sell per week? Another number, what price should they sell per TV set? Another number, what is the rebate from their original price, right? So you have to, once you find your absolute max or min for your problem, make sure you're really careful to answer the question that was asked. And from a business perspective, this answering the rebate is the most useful because it's the rebate that they decide, and that determines everything else, right? To maximize their revenue, first they'll decide on the rebate, so they'll reduce the price that they're charging by $125. That will result in selling 450 units. They originally were selling 350, right? So they're going to sell a lot more units. So now they know how many units to produce. And then they could calculate what their actual revenue would be if they wanted, right? We haven't even done that. The actual revenue, you could just take the 450, plug it back into the revenue function, and we'll tell you what their revenue would be per week. So today we covered all of section 4.7. We're still in the chapter of applications of differentiation, and these optimization problems are one application. So we covered, first of all, how to look at your word problem and recognize that it's an optimization problem, right? That's the first step so that you know to use the methods we discussed in this section. Then we covered a strategy. We had 6 steps that can be applied to solving these optimization problems, and we practiced it on some sample problems. And we saw part of this strategy was applying the methods we've learned earlier for finding either local extrema or absolute extrema.